Hello and welcome to the third video in this WAHEY series.
Aren't we all excited for this third instalment?
I'm Will Carne.
And I'm Carne.
And welcome to Nuclear Energy, we talk about all things nuclear and energetic. That's not strictly true.
Yeah,
okay,
that's not
let's get going immediately. Oh, if you've got any questions, ask in the comments.
As you always will, probably. Or complaints, yes. We get quite a few of those.
Yes.
Anywho, moving on to energy and mass. Now, with the threat of patronising you, E equals MC squared, a fact that our own physics teacher didn't seem to know somehow.
Didn't he?
No, he might have, put...
But this is Einstein's, of course, famous equation linking mass to energy with the constant C, 3 times 10 to the 8 meters per second squared.
Squared? MC squared, yeah, good. I'm glad we're on the same page. Good. Literally. An example of this in nuclear terms is annihilation, where a particle and an antiparticle meet, producing two photons with energy MC squared, where M is the mass of the original particle and antiparticle pair. Yep. Lovely stuff.
This is all from last year, but you need to know it all. But luckily, there are very handy videos on all of that to recap.
Oh, whose handy videos would that be?
I don't know.
They're lovely chaps, I've heard.
In alpha decay, the energy released is shared between the nucleus and the alpha particle.
Conservation of momentum will show it to be inversely proportional to their masses.
In beta decay, the energy is shared between the particle, nucleus, and neutrino, antineutrino.
And in electron capture, the emitted neutrino carries away released energy, and at times so does an X-ray.
Yes, now you may recall the strong nuclear force and its effects in pulling particles together.
Ooh, lovely stuff. It is strong, obviously, as it overcomes the repulsion from like charges, or poshly, the electrostatic repulsion.
But remember, it must become repulsive from about 0.5 femtometers or less. Otherwise, the nucleus would implode.
Which would be way cooler, but we wouldn't all exist to think about it. So, well. Moving on to binding energy now. The binding energy of the nucleus is the work that must be done to separate the nucleus into its constituent protons and neutrons.
Yeah, when a nucleus forms, energy is released, as effectively the strong nuclear force does the work.
Therefore, the mass of the nucleus is less than the separated nucleons due to conservation of energy laws.
The mass defect, delta M, of a nucleus is defined as the difference between the mass of the separated nucleons and the mass of the nucleus.
For X with mass number A and proton number Z, the mass defect equals Z multiplied by the mass of the proton plus A minus Z multiplied by the mass of the neutron, minus the mass of the nucleus. There you are.
Yes, so to find the binding energy of the nucleus, which would be helpful, it's just delta MC squared. Ah, that's familiar.
Delta MC squared, that's interesting. Yeah. That's a few things to note just before you dive into it. The atomic mass is given in terms of U, where 1 U is 1.661 times 10 to the minus 27 kilograms, or a 12th of the mass of an atom of carbon-12. So it's the scale they use. Using Einstein's equation again, you find it is equal to 931.3 mega electron volts of energy.
Yes, here A can be thought of as the magnitude of mass or energy. This perhaps is overcomplicating it, but it might help.
Basically, if you are given something in kilograms, convert it to U, then carry on. Just convert it straight away.
The binding energy per nucleon of a nucleus is the average work done per nucleon to remove all the nucleons from the nucleus for a measure of the stability of the nucleus.
This can be displayed on a lovely graph.
Yes, thank God. Now, you will be used to it the other way up, but we've been badgered by a badger to flip it upside down for reasons that will soon become clear.
It is a graph of binding energy per nucleon in mega electron volts against mass number A.
The maximum value is 8.7 mega electron volts per nucleon, which is between about when A is 50 or 60. And it's actually iron.
Yes, iron. Very good. Fe.
56?
56, yep, I think so.
Yep.
Just looking at a little graph here.
We have a periodic table.
We've upped our ante a bit.
We do.
Therefore, nuclei with mass numbers in this region are the most stable, as you need the most energy to separate them. Nuclear fission is where you have large unstable nuclei which split into 2 or more stable fragments. Usually 2, increasing the binding energy.
Nuclear fusion is where you have a small nuclei that fuse together to form a larger nucleus, giving a nucleus with more binding energy per nucleon, up to a nucleon number of around 50.
The reason we do the graph down, it makes it look nicer to aspire than to aspire to be at the bottom. Really, it's just I said bottom.
Fission and fusion.
Fish and chips. When fission is caused, for example, by the introduction of a neutron, it is called induced fission.
You can do this to uranium-235, making it become plutonium-239.
The second fissionable material.
Oh, that's handy.
Fission like this releases energy and 2 or 3 neutrons.
Fission neutrons, those produced, can collide with other uranium-235 nuclei to cause further fission. And therefore, a chain reaction.
Copyright. The energy released is massive and uncontrolled. The process will form a big, what's the word? I think it's called a bomb.
boom.
Boom, boom, boom.
Energy is released because the fragments repel each other, as they are both positively charged with enough force to overcome the strong nuclear force.
Therefore, the fragment nuclei and fission neutrons gain kinetic energy.
The new nuclei have more binding energy, so are more stable.
If asked, then the energy released is equal to the change in binding energy, because it is.
If then asked to write an equation for the reaction, check the energy or mass before with that after, and any left over will be the energy released, sometimes called Q or delta mc squared, where delta m is the mass defect from earlier.
Fusion is similar, where two lighter nuclei combine, making them more stable.
Yes, fusion can... and the energy released is equal to the increase in binding energy.
Fusion can only occur if the two nuclei collide at high speed, enough to overcome the electrostatic repulsion forces between them, and so enough to interact with the strong nuclear force that binds them.
An example of fusion is solar energy.
Solar energy. Protons fuse together to form hydrogen and then helium.
For each helium nucleus formed, 25 mega electron volts of energy is released, or about 6 mega electron volts per proton.
For the high speed, you need extremely high temperature, so electrons are stripped from the atoms, leaving matter referred to as plasma.
Sounds cool, doesn't it? Plasma.
Plasma.
Thermonuclear reactors.
Let's moving on.
A reactor contains fuel rods spaced evenly in steel called a reactor core. Sounds cool, doesn't it? Core.
Right. The reactor core contains control rods and a coolant as well as fuel rods.
It's connected by steel pipes to a heat exchanger where it turns into steam, driving turbines, turning the electricity generators into power stations.
Lovely stuff. When uranium is used in the fuel rods, you use enriched uranium consisting mostly of uranium-238 and then 2 to 3% uranium-235, which is fissionable.
In comparison, uranium, normal, natural uranium, contains about 99% uranium-238.
So you really are enriching it quite a factor of 3. I'm doing my maths there. 3 divided by 1 is 3-ish.
Wow.
Well, 2 to 3, so it could be... Anyway,
yes.
200 to 300%.
1 times 3 is 3. Well done.
I would like a sticker now, please.
Control rods absorb neutrons. The depth in the core is automatically adjusted to keep the number of neutrons in the core constant, so that on average, exactly 1 fission neutron per fission event goes on to produce further fission.
This keeps the rate of energy release constant and therefore manageable.
If you put the control rods in further, then the number of fission events per second and the rate of energy release is reduced.
The fission neutrons need to be slowed down to cause further fission of uranium-235 nuclei.
Therefore, fuel rods are surrounded by a moderator to slow the neutrons by repeating collisions with the moderator atoms.
Not moderators for exams. They are way more evil.
They aren't, but whatever we were talking about before, are thermal reactors because the neutrons are slowed down to kinetic energies comparable to that of moderator molecules.
Comparable indeed. For a chain reaction, if the mass of the fissile material is uranium-235, must be greater than the minimum mass, the critical mass. Sounds cool, doesn't it? Critical.
This critical mass is related to the number of neutrons leaving the material or being absorbed.
Let's get critical. There are 2 types of thermal reactors that you need to know about. PWRs, or pressurized water reactors, and AGRs, advanced gas-cooled reactors.
PWRs have water in the reactor core acting as both a moderator and a coolant.
Handy. The fuel is typically uranium oxide in zirconium alloy cans, and the coolant temperature is about 600 degrees Kelvin, with a power output of about 700 megawatts.
Yes. Now, AGRs use graphite as the moderator and CO2 gas as the coolant. The fuel is typically uranium oxide in stainless steel cans, and the coolant temperature is around 900 Kelvin with a power output of around 1300.
PWRs operate in many countries, including the UK, but AGRs operate only in the UK. Of nuclear power. A nuclear reactor needs some safety features, as you can probably guess.
Yes. The reactor core, a thick steel vessel designed to withstand high pressure and temperature and absorb beta radiation, neutrons and some gamma radiation.
Placing the core in a building with concrete walls which absorb the neutrons and gamma radiation that escape the reactor core.
Yes, and every reactor has an emergency shutdown system designed to insert the control rods fully to stop fission completely. Here the control rods can be inserted fully.
Look at that. Sealed fuel rods are inserted and removed by means of robots, as they are far more radioactive after use because uranium only releases alpha, which can be absorbed by the cans, but after it emits beta and gamma radiation due to the neutron-rich fission products.
Also, spent fuel rods contain plutonium-329, which is very active alpha emitter.
Which is indeed. Radioactive waste is labelled with 3 levels.
High, including spent fuel rods with any unused uranium or plutonium.
They must be removed by remote control, robots, and stored underwater in cooling ponds for up to a year as they continue to release heat due to radioactive decay.
The rest of the material is stored in sealed containers and buried in geologically stable areas.
So don't go burying it somewhere near an earthquake fault line. That's probably a bad idea. Some countries mix the waste with molten glass and storing it in glass blocks underground called vitrification.
Long-term storage is an issue as nobody wants it near them.
Not really. And then there's another level of nuclear waste called, well, funnily enough, called medium level. which including the radioactive containers that the fuel was in.
These should be sealed in drums, encased in concrete, and stored in specially constructed buildings with walls of reinforced concrete.
And then the last level is low level radioactive
I feel we should have
waste.
done the other way around. Now it's a bit sad. We've got to low.
Just low. Apple bad. No, okay.
Carry on.
So lab equipment and protective clothing that were used in the plant itself. These should be sealed in metal drums and buried in large trenches, it says here.
So to sum up, put it in a hole
Can't
until
be a
you can
ditch.
decide what to do with
Can't be a ditch, has to be a trench.
it. It has got to be a large trench. Don't put it in your coat though if you have a trench coat.
Or don't put it in a ditch coat if you've got one of those as well.
What about if it
You
is
really
a
shouldn't
radioactive trench coat?
Then you bury a trench coat in a trench. Inside another trench coat, inside another trench.
I feel the instructions would be complicated.
The instructions are not clear. I got my hand caught in a ceiling fan while trying this.
Right. Okay.
Sorry.
Thank you for listening. It's been very nice. Join us next time for our last video, which is all on ideal gases.
Ideal, not, ideally, they would be, hey.
Bye.
I'm going. Bye. I'm being kind of dark and this has been Will. Bye.